Roughly 4.6 billion years ago, a ripple of chaos swept through the Orion arm of the Milky Way. Within a swirling storm of dust and gas, something extraordinary began. Not with a bang, but with a slow, patient dance of gravity. This was the beginning of our sun, the first spark of what would one day become our solar system. At first, it was nothing more than a turbulent cloud, a disk of shattered rock and frozen molecules, spinning endlessly in the void. But within that chaos, gravity was quietly sculpting the foundations of everything we now call home. Planets, moons, oceans, mountains, and eventually, life itself. For hundreds of millions of years, matter collided and merged in a process called accretion, the cosmic art of creation through destruction. Tiny mineral grains stuck together, forming pebbles, then boulders, then the first asteroids, drifting fragments that would one day coalesce into entire worlds. It was an age of violence and wonder, when every collision carried both the potential for annihilation and for birth. Yet, as our sun ignited fully into a blazing star, something unexpected began to happen. Some of these asteroids didn't collide violently at all. Instead, they drifted together in slow, graceful spirals, gently merging in what scientists now call the gentle clumping hypothesis. This discovery, confirmed billions of years later by NASA's New Horizons probe, revealed that not all creation came from cataclysm. Some came from patience, from gravity's quiet hand. Among the billions of fragments swirling around the young sun, one began to grow larger than the rest, a molten, restless sphere that would one day be called Earth. But before our planet could settle into the familiar blue world we know today, it endured an event so cataclysmic that it nearly erased its own existence. Astronomers believe that around 4.5 billion years ago, Earth was struck by another young planet, a body roughly the size of Mars. This name, at least the name we've given it, was Theia. The collision was unimaginable. Two worlds colliding at tens of thousands of kilometers per hour. The impact liquefied Earth's crust, turned entire continents into vapor, and blasted a storm of molten rock into orbit. And yet, from that destruction, something beautiful emerged. The debris thrown into space slowly gathered again, circling Earth until it coalesced into a glowing sphere, our moon, a silent witness to our planet's most violent birth. For centuries, scientists, philosophers, and poets have looked to that glowing orb in the sky and wondered, where did it come from? Was it captured by Earth's gravity, torn from our planet's crust? Or was it, as the giant impact hypothesis suggests, born from the ashes of a world that no longer exists? The answers to those questions are not just about the moon, they are about us. Because without that impact, without Theia's destruction, Earth as we know it would never have existed. Our planet's tilt, its tides, its climate, perhaps even the evolution of life itself, all trace back to that single world-shattering moment. But the story of Earth's beginning doesn't end there. After the fires cooled and the molten oceans hardened into crust, our planet faced centuries of relentless bombardment from asteroids and comets. Its skies rained molten iron, its seas boiled, its surface cracked and reformed again and again. From these brutal beginnings, Earth forged its identity, a world shaped by chaos, tempered by time. And then, something miraculous happened. From the poisoned air and molten stone, water began to fall. It rained for centuries, perhaps millennia, until the entire world was shrouded in a vast global ocean. Out of this endless storm, the first continents began to rise, volcanic islands breaking through the surface of the primordial sea. From there, the story unfolds not as myth but as science. The appearance of the first microorganisms, the creation of oxygen, the first ice ages, the slow march toward complexity and consciousness. But every chapter, every fossil, every drop of water leads back to this, the moment the cosmos chose to create something new, a place where matter could dream. In this series, we will travel back through billions of years of planetary evolution, from the fiery chaos of the Hadean Aeon to the first breath of life, through the cataclysms that nearly ended it all, and the transformations that gave rise to the world we know. It's a story written not in words, but in stone, in ice, and in light. A chronicle of destruction and rebirth, where every ending becomes a new beginning. And so, as we look up at the moon tonight, a silent fragment of an ancient catastrophe, we're really looking back at the moment Earth became Earth. The question is not how it happened. The question is, why did it happen here? Why did our small, fragile world survive, when so many others did not? This is the story of the birth of a world, and the long, improbable path that turned chaos into life. Part 1. The dawn of the solar system in the vast, rotating arm of the Milky Way known as Orion. A star began to form from the collapse of a giant molecular cloud. Gravity, indifferent yet inevitable, drew together the drifting particles of gas and dust until they ignited in a nuclear fire. Our sun, then a newborn star surrounded by the debris of its own creation, lit up the surrounding darkness. Around it spun a glowing disk of material, dense clouds of hydrogen, helium, silicates, and metals, endlessly colliding, fusing, breaking apart, and coming together again. It was chaos governed by invisible order, the same natural laws that, billions of years later, would determine the motion of planets, moons, and even us. At this stage, the solar system was more a storm than a structure. Vast swirls of vaporous matter orbited the young sun in concentric rings. Within these rings, grains of mineral dust began to stick together through static electricity and weak gravitational pull. They grew from microscopic particles into pebbles, pebbles into boulders, and boulders into planetesimals, the building blocks of worlds. This process, known as accretion, was slow but relentless. Each impact released bursts of heat, fusing matter together in flashes of molten light. Over time, a cosmic hierarchy emerged. The larger a planetesimal became, the stronger its gravity grew, drawing in more material. Some became the cores of the future rocky planets, Mercury, Venus, Earth, and Mars. Others remained fragments, forming the asteroid belt that still orbits between Mars and Jupiter today. For decades, scientists believed that these planetesimals grew primarily through collisions, violent impacts that fused smaller bodies into larger ones. But as computer modeling advanced, a problem emerged. The math didn't add up. The simulations showed that high-speed collisions should have shattered these growing bodies instead of helping them merge. Something was missing. In 2019, NASA's New Horizons spacecraft provided a clue. On its journey beyond Pluto, the probe flew past a strange, snowman-shaped object in the Kuiper Belt, a relic from the dawn of the solar system. It was called Ediacaran. Its form, two lobes connected by a narrow neck, defied the expectations of a world formed by violent impacts. Instead, it appeared to have merged slowly, almost tenderly, over time. This discovery gave rise to a new theory known as gentle clumping. Rather than smashing together, small particles within the early solar system likely formed clusters of loosely bound clouds. These clouds gradually collapsed under their own gravity, forming planetesimals without destruction. Creation, it seemed, could be quiet. Through this process, one particular planetesimal began to grow larger and denser than most. It orbited at the perfect distance from the sun, not too hot, not too cold, in a region astronomers would later call the habitable zone. Layer by layer, impact by impact, it gathered mass until it became a molten, churning sphere, the young Earth. But Earth's formation was only the beginning. The early solar system remained a battlefield. Asteroids and protoplanets collided in fiery chaos, their orbits shifting unpredictably. Among them was another large body, a world about the size of Mars, now known as Theia. Theia's orbit gradually decayed, bringing it ever closer to Earth. For millions of years, the two worlds danced around each other in a cosmic waltz, their gravitational fields distorting the space between them. Then, one day, the inevitable happened. Theia struck Earth. The impact was unlike anything seen since the birth of stars. The collision released energy equivalent to billions of nuclear bombs detonating at once. Earth's crust melted, vaporized, and scattered into orbit. The entire planet became a roiling sea of magma, its atmosphere transformed into a haze of glowing vapor. And yet, this cataclysm would define everything that followed. Much of the debris ejected into space remained trapped within Earth's gravitational pull, forming a glowing ring around the planet, not unlike the rings of Saturn today. Over time, those fragments began to gather again, colliding gently, fusing into a single massive sphere. This was the birth of our moon. When it first rose above Earth's horizon, it was 16 times closer than it is today, an enormous, fiery disk dominating the sky. Tides were monstrous, hundreds of meters high, reshaping coastlines daily. Its gravitational pull slowed Earth's rapid spin, extending the length of our days. The Earth-Moon system became locked in a dance that continues even now, the moon forever showing us one face as it slowly drifts away, centimeter by centimeter, each year. For ancient observers, had they existed, the sight would have been both terrifying and divine, a molten satellite circling a molten world. But to modern science, it was the moment when Earth truly became stable. The moon's presence would later regulate our climate, control our tides, and perhaps even aid the emergence of life. For centuries, humanity struggled to explain this connection. Three main theories arose, each elegant yet incomplete. The fission theory proposed that the moon was once part of Earth, torn away by its rapid spin. The capture theory imagined it as a wandering planet drawn in by Earth's gravity. The co-formation theory suggested that both worlds formed together from the same primordial disk. But the evidence, when we finally reached the moon in 1969, told a different story. When the Apollo 11 astronauts returned with 21.5 kilograms of lunar rock, and later missions brought hundreds more, scientists compared their composition to Earth's. The results were astonishing. The isotopes of oxygen in lunar samples matched Earth's exactly, suggesting a shared origin. Yet the moon lacked volatile elements like water, nitrogen, and hydrogen. It was drier, lighter, and strangely depleted. These clues pointed back to the giant impact. Only a collision of such magnitude could have burned away the moon's volatiles while mixing its material with Earth's mantle. From that chaos, a world emerged, not just Earth as we know it, but the moon that would illuminate its nights and shape its rhythms. And while we now think of that ancient impact as an ending, it was in truth the first beginning. From the ashes of Theia and the molten remains of Earth, a system of balance was born, one capable of weathering time, evolving, and eventually giving rise to life. The solar system, once a turbulent cloud of dust, was now becoming a family of worlds, each shaped by fire, gravity, and chance. But for our small blue planet, the story was only getting started. Part 2, the Hadean Earth. Oceans of fire. When Theia struck Earth, it didn't simply create a crater, it remade the planet. Everything that had once existed on Earth's surface was obliterated. The crust melted into a sea of incandescent magma, and even the atmosphere was torn away, replaced by a suffocating haze of vaporized rock. The young world glowed like a dying star, its surface radiating heat into the cold void of space. This was the Hadean Aeon, the first and most violent chapter in Earth's history, named after Hades, the Greek god of the underworld. It was a realm of constant inferno, where oceans of fire replaced the seas, and the very air shimmered with death. Yet, amid the chaos, something remarkable was beginning to happen. As the molten surface slowly cooled, fragments of solid crust began to appear, first as thin, unstable rafts of rock floating on a magma ocean, then as early protocontinents. Volcanoes erupted continuously, pouring rivers of lava into the atmosphere and belching out gases that would one day form the foundation of our sky. Carbon dioxide, nitrogen, methane, water vapor, and sulfur compounds. The air was toxic, heavy, and dense, a chemical fog hundreds of times thicker than the modern atmosphere. From space, the young Earth would have appeared as a smoldering orb of orange and black, its surface glowing through gaps in turbulent clouds of ash. But within this infernal world lay the seeds of something unexpected, the ingredients for life. As the magma oceans began to cool, water vapor released from volcanic eruptions started to condense in the atmosphere. First, it was a faint mist. Then came the first rain droplets sizzling instantly as they struck the still scorching ground. But the planet continued to cool. The rainfall grew heavier, denser, more relentless. For thousands of years, the skies poured water in an unbroken deluge. It was the longest storm in the history of the solar system. The rain fell over molten plains, across cooling basalt fields, and into massive depressions created by asteroid impacts. Steam rose in endless clouds. Eventually, the heat of the Earth's surface subsided just enough for the water to remain liquid. The first lakes and shallow seas began to form. Then, over millions of years, those seas merged into vast planetary oceans. Earth, once a world of fire, had become an ocean world, enveloped in a reddish haze of methane and carbon dioxide. The surface was barren, the waters acidic and hot, but stable enough for new chemistry to take root. And yet, scientists still wonder, where did all that water come from? For decades, the prevailing idea was that Earth's water arrived from space, delivered by icy comets and hydrated asteroids bombarding the young planet. It was an elegant theory, one supported by the logic that early Earth was too hot to retain any original water. But there was a problem. When scientists compared the deuterium to hydrogen ratio, the chemical fingerprint of water, from comets to that found in Earth's oceans, the numbers didn't match. Cometary water was heavier, richer in deuterium, and inconsistent with our planet's unique isotopic signature. Later, new measurements revealed that water trapped within asteroids, particularly those from the region between Mars and Jupiter, bore a closer match to Earth's. This suggested that much of our water could have come from asteroidal collisions, a process known as the late Veneer hypothesis. Yet even that explanation had its flaws. The timing was off. Earth's oldest rocks show evidence of liquid water existing 4.1 billion years ago, long before the supposed asteroid delivery. So where else could it have come from? A new idea began to take shape. What if Earth's water wasn't delivered from the outside, but released from within? Deep inside the mantle, hydrogen and oxygen had been trapped within minerals since the planet's formation. As the mantle melted and erupted through volcanic activity, those elements combined to form water, which then escaped into the atmosphere as vapor. Once the surface cooled enough, that vapor condensed and fell back down as rain, filling the basins and forming the oceans we now know. In other words, the Earth made its own water. This theory, still debated today, paints a more self-contained picture of our planet's evolution. That everything, from its oceans to its atmosphere, was born from the same primordial material that formed the planet itself. By around 4 billion years ago, the endless rains had sculpted a world covered almost entirely in water. There were no continents, only volcanic islands poking through the surface like scattered embers on a dark sea. The sky was tinted orange-red from methane. Lightning flashed constantly through dense clouds, igniting chemical reactions in the atmosphere. And beneath those stormy skies, in the depths of the new oceans, something was stirring. Hydrothermal vents along the seafloor spewed superheated, mineral-rich water into the ocean, creating tiny pockets of chemistry, natural laboratories where complex molecules could form. These were not yet living cells, but the first whispers of organic chemistry, the prelude to biology. Even as the planet cooled, it remained under siege. Massive asteroids still crashed into the surface, vaporizing oceans and melting rock. Each impact was a catastrophe, yet also a reset, reforging the planet's surface and perhaps driving the very reactions that made life possible. This relentless cycle of destruction and renewal would continue for hundreds of millions of years. Slowly, the Earth hardened. The magma crust thickened, the atmosphere stabilized, and the bombardments began to fade. From this inferno, a world capable of hosting life finally emerged. The Hadean Earth was over, and in its place, the stage was set for a new era, one of continents, oceans, and the first fragile stirrings of life. Part 3. The Archean Dawn. The first breath of life by 4 billion years ago, Earth had finally begun to calm. The molten tides of the Hadean had subsided, leaving behind a restless but solid crust. Steam had condensed into oceans that shimmered beneath a crimson sky, and the endless rain had given way to dense clouds that wrapped the planet in permanent twilight. It was a world without continents, without oxygen, and without color. A planet of stone, water, and vapor. This new era would be known as the Archean Aeon, from the ancient Greek archaeos, meaning the beginning. It marked the dawn of geology, chemistry, and eventually life itself. But to imagine that first spark of life, we must abandon all images of green landscapes or animals swimming in blue seas. The early Earth was nothing like that. Its oceans were acidic, its air toxic, and its land, when it existed, was nothing more than volcanic islands surrounded by boiling surf. The atmosphere was dominated by carbon dioxide, methane, ammonia, and sulfur, with virtually no free oxygen. Lightning storms raged for centuries, their flashes igniting chemical reactions in the sky that rained down complex molecules onto the seafloor. Somewhere within those depths, perhaps near the mouth of a hydrothermal vent, or within a shallow pool of mineral-rich water, the first organic chemistry took hold. At first, it wasn't life as we know it. It was chemistry playing with itself. Molecules linking and breaking apart, experimenting with patterns that, by chance, began to persist. From those reactions came the earliest forms of self-replication. Fragile chains of molecules capable of copying themselves, mutating, and surviving long enough to repeat the process. These were the precursors of life, the first RNA molecules, the ancestors of all genetic code. Scientists believe that RNA came before DNA, a single-stranded molecule that not only stored information but also catalyzed chemical reactions. It could copy itself, repair itself, and even direct the synthesis of simple proteins. Over millions of years, these RNA systems became more stable, giving rise to DNA, a molecule stronger and more secure, one that could preserve information through countless generations. From this transition, chemistry to genetics, emerged the first prokaryotic cells, microscopic organisms without nuclei known today as bacteria and archaea. They were small, simple, and astonishingly resilient. Within their tiny structures existed all the hallmarks of life: metabolism, replication, and evolution. These organisms lived where few things could. They clung to the edges of hydrothermal vents, fed on chemical reactions between rock and water, and thrived in darkness where volcanic heat replaced sunlight. They were chemosynthetic, drawing energy from iron, sulfur, and hydrogen rather than light. And they were everywhere. At the microscopic scale, the oceans of the Archean were teeming with these early microbes. Over time, they diversified, some forming colonies, others developing the ability to use sunlight itself as an energy source. That innovation changed everything. Somewhere around 3.5 billion years ago, a new lineage of microorganisms appeared, cyanobacteria, the first life forms capable of photosynthesis. Using sunlight, water, and carbon dioxide, they produced glucose for energy and oxygen as a byproduct. At first, that oxygen went unnoticed. It immediately reacted with dissolved iron in the oceans, creating vast quantities of iron oxide, which settled onto the seafloor in alternating red and gray layers. These deposits, known today as banded iron formations, are found on every continent and represent the chemical fingerprints of Earth's first photosynthetic life. Ironically, this oxygen, which would one day sustain animals, plants, and humans, was deadly to most organisms living at that time. To the early anaerobic microbes, oxygen was a toxin. But evolution doesn't pause for comfort. Over millions of years, cyanobacteria filled the oceans, transforming them both chemically and visually. The once green waters became clearer, the skies began to shift, and the foundations for Earth's future atmosphere were being laid. Meanwhile, geological change continued on the surface. The small volcanic islands that had once dotted the oceans began to merge through tectonic activity, forming proto-continents. These early landmasses, perhaps no larger than modern Greenland, were the seeds of future continents. One of the first known was Volbara, which formed around 3.6 billion years ago and left traces still found in South Africa and Western Australia today. Volcanoes continued to erupt across these new lands, releasing gases and minerals into the air and sea. Rivers of lava carved valleys. Ash fell into oceans, fertilizing the waters below. Over time, this balance between destruction and renewal created more stable conditions, giving microorganisms more environments to adapt to. By 3.2 billion years ago, entire microbial ecosystems had formed near the coastlines, sticky mats of bacteria that trapped sediments and built up layer by layer over centuries. These formations, known as stromatolites, looked like rocky domes rising from the shallow seas. But inside them lived entire worlds, dense communities of microbes, feeding, growing, and photosynthesizing under the sun. Today, you can still find living stromatolites in places like Shark Bay, Australia, living fossils unchanged for billions of years. It's difficult to overstate their importance. For over a billion years, stromatolites were the dominant life forms on Earth, shaping not only ecosystems but also the planet's chemistry. Through their photosynthesis, they pumped out enormous amounts of oxygen, gradually transforming the atmosphere. But oxygen didn't accumulate right away. For nearly a billion years, it was absorbed by iron and other reactive elements in the ocean. Only once those sinks were saturated could oxygen begin to escape into the atmosphere. When it finally did, it triggered one of the most significant transformations in Earth's history, the Great Oxidation Event. That event was still far in the future. For now, the Archean world remained alien. Its skies orange and hazy, its oceans green and heavy with metals, its continents small and scattered. But beneath the surface, in every droplet of seawater, life was quietly taking hold. It was microscopic, invisible, but it was everywhere, and in time it would change everything. Part 4, The Great Oxidation. Earth's first crisis. By 2.5 billion years ago, Earth had changed beyond recognition. The once green oceans were now filled with microscopic architects of transformation, cyanobacteria, the photosynthetic pioneers that had conquered nearly every sunlit corner of the shallow seas. For hundreds of millions of years, they had been quietly reshaping the chemistry of the world, molecule by molecule, breath by breath. Until that moment, Earth had been a planet without oxygen. Its skies were suffused with methane and carbon dioxide, its oceans thick with dissolved iron. The color palette of this ancient world was alien. The seas were dark green, the sky a murky orange, the land black and volcanic. But with every photon absorbed by cyanobacteria, the balance began to tip. Through photosynthesis, they split water molecules, releasing oxygen gas as a waste product. At first, that oxygen never reached the air. It immediately reacted with the abundant ferrous iron in the oceans, turning it into insoluble iron oxide, which fell to the seafloor in shimmering layers. Over time, these layers built up into vast geological monuments. Banded iron formations, alternating stripes of red hematite and gray chert, some stretching hundreds of meters thick. These formations tell the story of Earth's invisible revolution. For nearly a billion years, oxygen was produced and consumed entirely beneath the waves. The atmosphere above remained unchanged, toxic, dense, unbreathable. But nature has a way of exceeding its boundaries. Eventually, the oceans could no longer absorb the oxygen being produced. The iron ran out. The chemical sponges were full, and for the first time in history, oxygen began to leak into the atmosphere. At first, it was a whisper, a few parts per million, but soon it spread across the skies, reacting violently with the gases that had once dominated the air. Methane, a powerful greenhouse gas, was oxidized into carbon dioxide and water vapor. The delicate thermal balance of the planet was shattered. The world began to freeze. This was the Huronian glaciation, the first global ice age in Earth's history. Triggered by the rise of oxygen, it began around 2.4 billion years ago and may have lasted for more than 300 million years. Ice advanced from the poles to the equator, covering nearly the entire surface of the planet, even the tropical seas. Scientists call this event a Snowball Earth. Imagine a world locked in white silence, oceans sealed beneath kilometers of ice, temperatures plummeting far below freezing. To most of the life that existed then, oxygen was poison, and the cold a death sentence. Vast populations of anaerobic microbes perished. It was the first mass extinction in Earth's history. But not everything died. Life, as it always does, adapted. In the hidden warmth of hydrothermal vents, within subglacial lakes, and even inside pockets of ice, microbial life endured. Some species developed mechanisms to survive the new oxygen-rich environment. They learned not to fear oxygen, but to use it. This innovation would change evolution forever. For while oxygen had brought catastrophe, it also carried potential. It was far more energetically efficient than any other chemical fuel available. Organisms that learned to harness oxygen through aerobic respiration could extract nearly 20 times more energy from the same amount of food. This was evolution's greatest leap, a biological revolution hidden inside a planetary crisis. Meanwhile, the planet itself continued to shift. The appearance of free oxygen triggered profound changes not just in biology, but in geology and atmosphere alike. The oxygen molecules rising through the air began to interact with ultraviolet radiation from the sun, forming a thin but vital layer of ozone, O3, high above the planet. For the first time, Earth had a shield, one capable of blocking deadly UV radiation, making the surface more hospitable for future life. It was an extraordinary paradox. The event that nearly destroyed life also made complex life possible. As the glaciation persisted, volcanoes continued to erupt beneath the ice, releasing carbon dioxide into the atmosphere. Over millions of years, the greenhouse effect slowly returned. The ice began to melt. The planet thawed. When the snowball finally cracked, Earth emerged profoundly changed. The once orange skies were now blue. The oceans, stripped of their iron, turned from green to clear turquoise. The continents that had formed during the late Archean, vast landmasses like Kennerland, began to fragment under the motion of tectonic plates. Rivers carved through the melting ice, carrying nutrients to the seas below. The aftermath of this planetary winter gave rise to new ecosystems, oceans rich with minerals and newly oxygenated waters. It was, in every sense, a rebirth. But even as oxygen transformed the world, its presence remained unstable. Geological evidence suggests that the atmosphere's oxygen levels fluctuated wildly for hundreds of millions of years after the Great Oxidation event. It would take almost another 2 billion years before the air stabilized at levels capable of sustaining large, complex organisms. Still, the blueprint was set. The planet had learned to breathe. The cost had been immense. Oceans frozen, species wiped out, the very surface reshaped. But from that crucible came resilience. The stage was ready for the next chapter in Earth's story. The slow rise of complex cells, eukaryotes, and the dawn of multicellular life. The world had endured its first true apocalypse, and it had survived. Part 5, The Rise of the Eukaryotes. The cells that changed the world when the great ice sheets of the Huronian glaciation finally retreated, around 2.1 billion years ago, the Earth exhaled. The air was still thin, but breathable for a new kind of organism, one born from catastrophe. For hundreds of millions of years, the planet had been dominated by the simple, ancient life of prokaryotes. Single-celled bacteria and archaea, small enough to fit thousands within a grain of sand. They had built the foundations of life's chemistry, but the world was ready for something more complex. From that frozen silence emerged the eukaryote, a cell unlike any that had existed before. To understand what made it special, imagine a microscopic revolution. The eukaryotic cell contained, for the first time, an internal architecture, a nucleus that protected its genetic material, and organelles that performed specialized functions. Inside these tiny compartments, chemistry became organized, efficient, and scalable. It was as if evolution had gone from huts to cities. But how did such a leap occur? The answer, scientists believe, lies in one of the most extraordinary partnerships in Earth's history, an act of biological symbiosis. Somewhere deep in the Proterozoic oceans, An ancient archaeal cell engulfed a smaller bacterium, not to consume it, but to cooperate with it. The smaller organism was a specialist in energy production. Instead of being digested, it took up residence within its host, gradually becoming an integral part of its metabolism. That internal guest evolved into what we now know as the mitochondrion, the powerhouse of the cell. Through this alliance, early eukaryotes could harness oxygen to produce vastly more energy than their anaerobic predecessors. It was a quiet deal between two microbes, but it would change the destiny of life on Earth. With this newfound efficiency came potential. Eukaryotic cells could grow larger, store more DNA, and perform more complex processes. They could specialize, diversify, and, in time, cooperate with one another. The door to multicellular life had opened. The fossil record tells us that eukaryotes appeared around 1.9 billion years ago, during a period of relative calm after the planet's long freeze. The air was rich in oxygen compared to the Archean, the oceans clearer and cooler. In these new conditions, microscopic eukaryotes thrived. Some evolved rigid cell walls and chloroplast-like structures, developing primitive photosynthesis of their own. Others became predators, engulfing smaller cells for food, the first stirrings of ecological interaction. One of the earliest known eukaryotic fossils is a mysterious spherical microfossil called Grippania spiralis, found in rocks dating back nearly 2 billion years. It formed spiral, ribbon-like tubes several centimeters long, large enough to be seen without a microscope. Its size alone was revolutionary, a direct consequence of eukaryotic complexity. Alongside it appeared other enigmatic forms, collectively known as acritarchs, microscopic fossils of uncertain origin. Some were smooth, others spiny, some resembling pollen grains. They likely represented the earliest algae, photosynthetic eukaryotes drifting through the sunlit shallows, transforming the seas into living tapestries of color and chemistry. By 1.8 billion years ago, the oceans teemed with these new forms. Some were green algae, precursors of plants. Others were heterotrophic organisms that fed on others, precursors of animals and fungi. The eukaryotic family tree was branching, even if its leaves were still invisible to the naked eye. Meanwhile, the planet's surface was undergoing its own transformations. Continents drifted and merged to form a massive supercontinent known as Columbia, also called Nuna, around 1.8 billion years ago. This landmass spanned nearly half the planet, stretching from pole to pole, surrounded by vast, nutrient-rich oceans. Weathering from its red, iron-rich soils fed the seas with minerals, fueling blooms of early photosynthetic life. But despite this apparent progress, evolution seemed to slow. For nearly a billion years, Earth entered what scientists call the boring billion, a time of environmental stability and biological stagnation between 1.8 and 0.8 billion years ago. The name is deceptive. The boring billion was not lifeless. It was stable, perhaps too stable. Oxygen levels plateaued. Nutrient cycling reached equilibrium. There were no massive extinctions or dramatic climatic shifts. The continents drifted lazily, the climate remained temperate, and the oceans stratified into layers, oxygenated at the surface, anoxic below. Life persisted, but it did not yet flourish. And yet, beneath the apparent monotony, subtle revolutions were unfolding. Eukaryotic cells were experimenting, learning how to cooperate, how to specialize, and how to reproduce sexually. That last innovation was perhaps the most significant of all. Sexual reproduction introduced genetic recombination, the ability to mix DNA from two individuals to create offspring with new combinations of traits. It was evolution's accelerant, allowing adaptation to happen faster than ever before. With every generation, nature could test new possibilities. By the end of the boring billion, around 1 billion years ago, the first true multicellular organisms began to appear. Fossils like Bangiomorpha pubescens, a red alga discovered in Arctic Canada, show that complex, multicellular life, with specialized reproductive cells, had already evolved. This humble alga, existing over 1 billion years before the dinosaurs, represents the earliest known instance of sexual reproduction in the history of life. Meanwhile, microscopic green seaweeds such as Proterocladus antiquus, discovered in Chinese rocks of similar age, hint at the earliest ancestors of modern plants. Though only millimeters long, they were the first to truly capture sunlight in the way forests and grasslands do today. The world was changing again, slowly but inexorably. Beneath the calm surface of the Proterozoic seas, evolution was gathering momentum, preparing for the next leap. The eukaryotes had laid the foundation. They had turned energy into structure, structure into cooperation, and cooperation into complexity. The blueprint for animals, plants, and fungi was written. All that was missing was the spark to ignite it. And soon that spark would come in the form of climate chaos, global ice, and an evolutionary explosion that would give rise to the first animals. Part 6, the Cryogenian Earth. Planet Snowball. The Earth had known fire. It had known oceans of stone, skies of poison, and worlds without breath. But nothing in its long history compared to what came next. Roughly 720 million years ago, the planet began to freeze. Not a mild winter, not a regional chill, but a transformation so complete that even the equator glittered with ice. This was the Cryogenian period, a time when Earth became, quite literally, a snowball adrift in space. The transition from the mild stability of the boring billion to this planetary catastrophe was sudden and violent. Oxygen levels had risen. The supercontinent Rodinia, which had drifted together during the previous era, began to crack apart, its pieces grinding against one another, opening new ocean basins. These rifts unleashed vast amounts of weathered rock and minerals into the sea, and with them, carbon was drawn out of the atmosphere. Carbon dioxide, the planet's most important greenhouse gas, began to plummet. With less CO2 to trap heat, the world cooled. Ice formed at the poles, spreading like a contagion across continents and oceans alike. The more the ice advanced, the more sunlight it reflected back into space, a feedback loop called the albedo effect. It was unstoppable. Within a geological blink, the entire planet froze over. Glaciers stretched thousands of kilometers. The seas beneath them were capped by ice several kilometers thick. Even near the equator, frozen waves reached the horizon. From orbit, the Earth would have looked like a perfect pearl, silent, white, and lifeless. But it wasn't lifeless. Not entirely. Beneath the ice, microbial life endured. Some found refuge near volcanic hot springs, where the planet's inner heat melted pockets of water through the ice. Others survived in deep ocean vents, thriving in darkness where chemical energy replaced sunlight. Life had always been patient. It knew how to wait. Still, the Cryogenian was a planetary trial. For tens of millions of years, the Earth remained locked in this deep freeze. Some scientists believe the global temperature fell as low as -50 degrees Celsius, with the oceans sealed from the air. The atmosphere itself thinned, dry and crystalline. Methane, once a powerful greenhouse gas, had frozen into clathrate ice, buried beneath the snow. The world should have stayed dead. But deep beneath the ice, volcanoes were still burning. As glaciers scoured the continents, volcanic eruptions continued to pump carbon dioxide into the atmosphere. With the oceans frozen, there was no way for this CO2 to dissolve or be reabsorbed. It began to build molecule by molecule, forming a greenhouse blanket that thickened over millions of years. And then, abruptly, everything changed again. When the atmosphere reached a critical concentration of carbon dioxide, perhaps hundreds of times today's levels, the planet began to thaw. The ice retreated at astonishing speed, melting in great torrents that flooded the continents. The frozen oceans boiled with supercharged storms. The global average temperature may have swung from subarctic to tropical in only a few thousand years, an instant geologically speaking. It was Earth's most dramatic climate reversal. The thaw unleashed colossal floods that stripped mountains and carved new river systems. Minerals trapped in ice poured into the oceans, fertilizing them with phosphorus and iron. Algal blooms erupted across the seas, turning the world green again. But what of life? What had survived the freeze? The survivors were ancient, microscopic, and few, but they carried the genetic toolkit for everything to come. Among them were early eukaryotes, descendants of the Great Cellular Revolution. Hidden beneath glaciers, they had weathered millennia of darkness. Now, as sunlight returned to the oceans, they multiplied with explosive vigor. This resurgence of photosynthetic life oxygenated the seas anew, paving the way for evolutionary innovation. For the first time, multicellular organisms began to appear in greater variety. Simple colonies of cells began to organize, dividing labor, specializing, forming tissues. The cryogenian freeze had been a crucible, and out of it, life emerged stronger. As the ice retreated, the planet's continents rearranged themselves once again. By 620 million years ago, the drifting fragments of Rodinia had coalesced into a new supercontinent, Pannotia, gathered mostly in the southern hemisphere. Around it stretched a vast global ocean called Panthalassa. The climate warmed, glaciers melted, and shallow seas flooded the continental shelves. For the first time in hundreds of millions of years, the world was warm, wet, and alive. In these rejuvenated oceans, the earliest multicellular animals began to appear, soft-bodied, simple, and alien. They had no bones, no shells, no hard parts at all, only thin membranes of tissue that floated gently in the currents. But in those tissues lay the first outlines of modern biology: organized cells, symmetry, and movement. These strange creatures would soon dominate the seas of the next era, the Ediacaran period, the prelude to the Cambrian Explosion. The Snowball Earth had come and gone. The planet had nearly frozen to death, only to emerge into an age of light and complexity. It was the second time in Earth's history that catastrophe had given birth to progress. The first had been oxygen. The second was ice. And soon both would meet in the first ecosystem recognizable as life as we know it. Part 7. The Ediacaran World. Gardens of the first animals. When the great cryogenian ice sheets finally melted, the world awoke to a new dawn. The year was roughly 635 million BCE, and the planet, once a frozen tomb, had transformed into a humid greenhouse world. Oceans stretched wide and warm, fed by the mineral runoff from glaciers that had scoured the continents for millions of years. For the first time in eons, sunlight streamed uninterrupted to the seafloor. This new era, known as the Ediacaran period, marked a turning point in Earth's history. After nearly 4 billion years of chemical and microbial evolution, the stage was finally set for something unprecedented: large, complex, multicellular life. But what rose in those ancient seas was unlike anything alive today. In the depths, on the soft, silted floors of the Ediacaran oceans, new creatures began to bloom. They did not swim or crawl. They did not bite, hunt, or hide. Instead, they grew, anchored to the seabed like living fronds, absorbing nutrients directly from the water. Their bodies were soft and symmetrical, leaf-like, quilted, and ethereal, forming the first true ecosystems in Earth's history. Imagine walking across that ancient seafloor. There is no coral, no fish, no kelp. The landscape is alien and silent, illuminated by filtered sunlight drifting through the water. Around you rise shapes that defy modern classification. Towering, feather-shaped organisms, broad discs pressed into the sand, delicate veined forms rippling in the current. This was the world's first animal garden, a biosphere both familiar and profoundly strange. Among its inhabitants was Fractofusus, a spindle-shaped organism that could reach over a meter in length. It lay flat upon the seafloor, branching into fractal patterns, each part a mirror of the whole. Nearby grew Charnia, elegant and fern-like, anchored to the sediment by a bulbous holdfast. Its fronds, sometimes over half a meter tall, waved gently in the slow currents. Beside them drifted Bradgacia, shaped like a head of cabbage, Ranhaea, a many-petaled fan, and Tribrachidium, a small, trisymmetrical creature unlike anything before or since. These forms, collectively known as the Rangeomorphs, represented an entirely new experiment in biology, one that may have had no direct descendants. The Ediacaran creatures lacked mouths, organs, or skeletons. Instead, they absorbed nutrients passively from the surrounding water, or from thin microbial films that covered the ocean floor. Scientists believe they practiced osmotrophy, feeding by diffusion through their surfaces, a strategy made possible by the rich, oxygenated seas of their time. But not all life was rooted. Some Ediacaran organisms could move, slowly, deliberately, leaving faint trails across the sediment. Among these was Dickinsonia, an oval creature up to a meter long, with rib-like segments running down its body. Fossil evidence shows that Dickinsonia moved across microbial mats, consuming the organic material beneath and leaving behind ghostly impressions of its path, as though it grazed the seafloor like an animal. For decades, scientists debated whether Dickinsonia was a fungus, a lichen, or something else entirely. Then, in 2018, organic analysis revealed traces of cholesterol within its fossils, a molecule unique to animals. It was finally confirmed Dickinsonia was one of the earliest true members of the animal kingdom. Alongside it lived Cambriella, another enigmatic form with a low, oval shell and a front ridge that may have functioned like a mouth. Traces of scraping marks found near its fossils suggest it fed on microbial mats using a primitive tongue-like organ, similar to the radula of modern mollusks. Cambriella, then, may represent the earliest known bilaterian, an organism with left and right symmetry, a front and a back, a body plan that all complex animals, including humans, would later inherit. As the Ediacaran seas flourished, their oxygen levels rose to unprecedented heights. For the first time, the planet's atmosphere may have reached nearly 10% of modern oxygen levels, enough to sustain multicellular metabolism. The oceans were shallow, calm, and stable, bathed in warm currents and shielded by the ozone layer that had formed during the Great Oxidation billions of years before. It was the perfect cradle for complexity. And yet, the Ediacaran world was not static. Over the next 70 million years, these strange life forms evolved, spread, and diversified. Fossil beds in Australia, Newfoundland, and Russia record entire communities of them, each layer capturing a new stage in the unfolding story of multicellular life. Some Ediacaran creatures even show signs of reproduction, with smaller individuals clustered around larger parents, hinting at the first coordinated biological life cycles. Still, there was something fragile about this world. These organisms lacked hard parts or defenses. They depended on an environment of remarkable stability. Their very existence was tied to the chemistry of the oceans, a balance that could easily be disturbed. And disturb it the Earth soon did. Around 541 million years ago, the Ediacaran biosphere began to fade. The soft-bodied creatures disappeared from the fossil record, replaced by something new, organisms with shells, skeletons, claws, and teeth. The planet was entering a new phase, a time of competition, predation, and rapid diversification. The Ediacaran world had been a peaceful prelude, a quiet experiment before the explosion to come. For tens of millions of years, its organisms ruled a world without conflict. But evolution never stays still for long. From their soft forms would arise the hard, armored life of the Cambrian Explosion, the moment when Earth's biosphere erupted into color, movement, and warfare. The Ediacaran period ended not with extinction, but with transformation, its delicate gardens giving way to the first truly modern ecosystems. Part 8. The Cambrian Explosion. The day the world came alive about 541 million years ago, something extraordinary happened. The Earth, long home to simple, soft-bodied creatures, awoke. In a span of just a few tens of millions of years, a mere instant in geological time, life underwent one of its most dramatic transformations. The seas, once still and silent, exploded with diversity. This was the Cambrian Explosion, the dawn of animal life as we know it. Before the Cambrian, the Ediacaran seas had been quiet gardens, populated by creatures that absorbed nutrients or drifted softly in the currents. But by the start of the Cambrian period, life had learned to move, hunt, and defend. The world's first predators appeared, and with them the first armor, the first eyes, and the first evidence of struggle. The planet's surface, too, was changing. The continents were splitting apart and drifting, creating shallow coastal seas that teemed with nutrients. Oxygen levels in the oceans rose once again, and chemical cycles became more dynamic. For the first time in history, energy flowed through ecosystems on a massive scale. This surge in oxygen may have been the spark that ignited evolution's greatest fire. In these new seas, the first complex animals evolved, creatures that would lay the foundation for nearly every major group alive today. Biologists call them phyla, the great branches of the animal kingdom. Nearly all of them appeared during this one incredible window of time. Among the earliest were the arthropods, ancestors of insects, spiders, and crustaceans. Their bodies were divided into segments and encased in protective shells made of chitin. They moved with articulated limbs, tools of precision and power. One of the most iconic was trilobite, a creature with a hard, segmented exoskeleton and compound eyes. Trilobites would go on to dominate the seas for 270 million years, leaving behind fossils on every continent. Then there were the anomalocaridids, like Anomalocurus, the terror of the Cambrian seas. Up to a meter long, it was one of the largest animals on Earth at the time. It swam with rippling lobes and grasped prey with two spined appendages, feeding with a circular, tooth-lined mouth. For the first time, evolution had produced an apex predator. In response, prey evolved defenses. Some developed shells made of calcium carbonate, the first skeletons in the fossil record. These small, shelled creatures, collectively called the small shelly fauna, represent the earliest use of hard body parts in evolutionary history. The invention of the shell changed everything. It allowed animals to burrow, hide, and protect themselves from attack. Another innovation followed soon after: eyes. For hundreds of millions of years, life had sensed only light and dark. But during the Cambrian, vision evolved rapidly and independently across multiple lineages. Trilobites had complex compound eyes, capable of detecting movement and form. Other creatures developed simple lenses that could focus light. Suddenly, the ocean was no longer a world of shadows. It was a battlefield of sight and strategy. Predators chased prey. Prey hid, evolved camouflage, or burrowed into the seafloor. This escalating evolutionary arms race, called the Red Queen dynamic, drove the diversity of life to explode in complexity. Every adaptation demanded a countermeasure. Every invention invited another. Fossil beds like the Burgess Shale in Canada and the Changjiang Formation in China capture this moment in stunning detail. There, soft-bodied creatures were buried in fine silt, their forms preserved for over 500 million years. From these fossils, we can reconstruct an entire alien ecosystem. In the Burgess Seas swam creatures like Opabinia, with 5 eyes and a long, flexible trunk tipped with claws. Nearby drifted Hallucigenia, a tiny worm bristling with spines and tentacles, so bizarre that early reconstructions placed it upside down. Wawaxia, covered in overlapping scales, crawled across the seafloor feeding on detritus. And above them all, Anomalocurus hunted, a sleek shadow cutting through the light. In the sediment below, the first burrows appeared, evidence that animals were now digging, reshaping their environments, and creating complex ecosystems. The seafloor became alive with tunnels, trails, and feeding marks. Life was no longer static. It interacted, competed, and built. The Cambrian Explosion was not just an expansion of forms. It was an explosion of behavior. Within only a few tens of millions of years, every fundamental body plan had evolved. Worms with internal skeletons, mollusks with shells, echinoderms with radial symmetry, and the earliest chordates, primitive ancestors of vertebrates. One of these tiny chordates, Pichia gracilens, wriggled through the sediment of the Burgess Seas, propelled by a flexible rod down its back, the first known notochord. It was the blueprint for the spinal column, and from it, in time, all fish, reptiles, birds, and mammals would descend. The Cambrian world was vibrant, colorful, and full of motion. Sunlight filtered through warm, shallow seas, illuminating reefs of sponges and algae. Swarms of trilobites scuttled across the seabed. Worms burrowed through the mud. Predators lurked in open water, and tiny filter feeders drifted in the currents. It was the first true biosphere, a self-sustaining web of energy and evolution. But even as life flourished, the planet was still volatile. Volcanic eruptions, shifting continents, and changing climates periodically threatened to undo what evolution had built. And yet, life endured, each crisis pushing it toward new innovations, new designs, and greater resilience. The Cambrian Explosion marked not just the birth of animal diversity, but the beginning of ecological complexity. It was the moment when life began to shape the planet as much as the planet shaped life. The seas would never be empty again. Part 9. The Ordovician Earth. The age of expansion, the Cambrian Explosion had filled the seas with wonder. Trilobites, worms, predators, and reefs bursting with color and motion. But it was only the beginning. When the Cambrian period ended around 485 million years ago, the next chapter began. The Ordovician period, a time when life didn't just diversify, it expanded across every corner of the oceans, forming the planet's first truly global ecosystems. This was the age of expansion, when the sea became a cathedral of life. The Earth itself was transforming. The supercontinent Gondwana dominated the southern hemisphere, while smaller landmasses, Laurentia, Baltica, and Siberia, drifted across the equator. Vast shallow seas flooded their margins, creating warm, sunlit environments perfect for life. These continental shelves became the nurseries of evolution, teeming with new organisms that would define the Paleozoic world. Beneath waves of clear blue water, reefs began to rise, not yet built by coral, but by sponges, bryozoans, and cyanobacteria. They formed towering structures of limestone and microbial mat, alive with swarming invertebrates. For the first time in history, the oceans possessed structure, layers, and communities, from the muddy floor to the sunlit shallows. Dominating these seas were the trilobites, now numbering in the thousands of species. Some were hunters with spiked tails and serrated limbs. Others were gentle grazers, feeding on plankton or detritus. Their variety reflected a world of niches. Every possible way to live was being explored. Yet even the trilobites had rivals. The Ordovicians saw the rise of brachiopods, clam-like creatures with two shells, and bryozoans, colonial filter feeders that formed living mats across the seafloor. Mollusks diversified into early snails and cephalopods, the latter evolving into the orthocones, long, conical relatives of modern squids and nautiluses. Some orthocones grew over 6 meters long, becoming the top predators of their age. In the deeper waters, early jawless fish, the agnathons, appeared, covered in protective plates of bone. They swam slowly, filter feeding or scavenging the seafloor. Though primitive, these armored pioneers represented a revolutionary step. The first vertebrates, ancestors of all future fish, amphibians, and land animals. The Ordovician oceans were vast theaters of color and sound. Algae covered the seabed in green and gold. Schools of small invertebrates drifted through the water column. And in the shallows, clusters of organisms formed intricate food webs. Predators, scavengers, and grazers balanced in dynamic equilibrium. For nearly 40 million years, this world flourished in peace. Biodiversity tripled, creating what paleontologists call the Great Ordovician Biodiversification Event. It was the most significant expansion of marine life in history, a second evolutionary explosion, rivaling the Cambrian in scope but surpassing it in complexity. But beneath this flourishing world, the planet's heartbeat was changing. The continents were on the move. Gondwana, massive and restless, drifted slowly southward toward the pole. As it did, the global climate began to cool. Glaciers started to form along its southern edges, reflecting sunlight and accelerating the chill. The oceans cooled, currents shifted, and sea levels began to drop. At first, the changes were gradual. But then, around 445 million years ago, the Earth plunged into its first great mass extinction. As the glaciers spread, sea levels fell by more than 100 meters, draining the shallow continental seas that had nurtured so much life. Entire ecosystems vanished overnight. The cooling ocean held less oxygen, suffocating marine creatures adapted to warmth and stability. Nearly 85% of marine species perished, trilobites, brachiopods, and reef builders among them. It was the end of an era, the first global catastrophe to challenge the dominion of life in the oceans. And yet, even in extinction, evolution found opportunity. The survivors adapted to the cold. They evolved new metabolic efficiencies, new body plans, new defenses. When the glaciers finally melted and sea levels rose again, these survivors radiated into empty ecosystems, setting the stage for new dominance. The Ordovician ended as it had begun, with transformation. Life had proven it could endure climate catastrophe, adapt to change, and recover stronger than before. The oceans would never be the same again. From this great die-off emerged new players, armored fish, complex reefs, and the first tentative steps of plants and invertebrates onto land. The world was preparing for another leap forward, one that would carry life from the seas to the continents. Part 10. The Silurian World. Life finds the shore when the Great Ordovician Ice Age ended around 443 million years ago. The glaciers receded, the seas returned, and life once again began to bloom. The survivors of that first mass extinction inherited a world transformed. A cooler, clearer, and more oxygen-rich planet. This was the dawn of the Silurian period, a time when the oceans stabilized and, for the first time, life began to reach beyond them. The Silurian world was one of recovery and innovation. The shattered marine ecosystems of the Ordovician slowly rebuilt themselves, giving rise to new kinds of coral reefs, new fish, and, on land, the very first stirrings of vegetation. The continents had rearranged again. The vast supercontinent Gondwana still covered the southern hemisphere, while smaller landmasses, Laurentia, Baltica, and Siberia, drifted near the equator. Where they met, tropical seas stretched across shallow shelves, warm and fertile. In these golden waters, life reached new heights of complexity. The reefs of the Silurian were magnificent. No longer built just by sponges and stromatolites, they were now constructed by tabulate and rugose corals, forming the first true coral ecosystems. Towering structures of limestone teemed with creatures. Crinoids waving feathery arms to catch plankton, bryozoans forming lace-like colonies, and brachiopods carpeting the seabed like living shells. But the real revolution was happening among the fish. The earliest vertebrates, jawless fish from the Ordovician, had survived the Great Extinction, and during the Silurian they diversified dramatically. Some developed heavy bony armor, becoming the ostracoderms, small, bottom-dwelling fish plated like living shields. Others evolved something entirely new, jaws. It was one of the greatest evolutionary innovations in history. From simple gill arches used for breathing, nature reshaped the front of the head into a tool for biting, grasping, and defense. These first jawed fish, the placoderms, appeared in the Silurian seas, armored hunters with teeth-like plates that could shear through prey. They were powerful, agile, and intelligent for their time, the prototypes of all modern predators. With jaws came a new ecological balance. Predator and prey, chase and flight. The Silurian oceans became vibrant arenas of motion and survival. While life flourished underwater, something miraculous was beginning to unfold above the waves. For billions of years, the continents had been barren, rocky wastelands scoured by wind and rain. But now, for the first time, life was moving onto land. The pioneers were plants. Around 430 million years ago, the first vascular plants appeared, small, moss-like organisms that grew in damp coastal soils and riverbanks. Among the earliest was Cooksonia, a simple, leafless stem tipped with tiny spore capsules. Barely a few centimeters tall, it was humble, yet revolutionary. Cooksonia had developed vascular tissue, allowing it to transport water and nutrients internally. This adaptation freed it from the constant grip of the tides. For the first time, a living organism could draw sustenance from the soil and reach upward toward the sun. As these early plants spread, they began to alter the planet itself. Their roots broke down rock, releasing minerals into streams and oceans. Their photosynthesis consumed carbon dioxide and released oxygen, gradually changing the atmosphere. The very chemistry of the Earth was shifting to make way for the land biosphere. And where plants went, animals followed. The first land dwellers were not vertebrates but arthropods, distant relatives of insects and spiders. Fossilized trackways reveal that millipede-like creatures and primitive scorpions had begun to explore damp shorelines. They likely hunted smaller invertebrates or fed on decaying plant matter, forming the earliest land-based food webs. These pioneers lived in a world still dominated by the sea. Inland, the continents remained desolate, their skies streaked with volcanic ash and dust. But along the coasts, green life crept steadily forward, binding the soil, capturing sunlight, and weaving the first terrestrial ecosystems. Back in the oceans, the balance of power continued to evolve. The Silurian reefs grew larger and more complex, home to an explosion of marine diversity. Cephalopods, ancestors of squids and octopuses, prowled the reefs with coiled shells. Eurypterids, or sea scorpions, reached monstrous sizes, some over 2 meters long. They ruled the shallow seas and river mouths, their armored bodies gliding with eerie grace. These apex predators symbolized the Silurians' dual nature, peaceful recovery and ruthless adaptation. The world was both beautiful and dangerous, and increasingly interconnected. By the end of the Silurian, around 419 million years ago, the continents of Laurentia and Baltica collided, forming the first great northern supercontinent, Euramerica. This collision raised new mountains and reshaped global climates, creating rivers, floodplains, and deltas, new habitats waiting to be filled. The stage was set for the next great leap, the colonization of land by larger plants and animals, and the birth of forests, insects, and the first amphibious vertebrates. The Earth was becoming not just a planet of oceans, but a planet of life in all directions. Part 11, The Devonian World. The age of fish, the Silurian had brought life from the sea to the shore. But in the era that followed, the Devonian period, beginning around 419 million years ago, life didn't just adapt. It conquered. The Devonian was a world in transformation, an age when the oceans teemed with armored fish, plants grew into forests, and animals began their first true steps onto land. It was the age of fish and the dawn of ecosystems we would recognize today. The continents had drawn closer together, forming two great landmasses, Gondwana in the south and Euramerica in the north. Between them lay wide tropical seas, shallow and sunlit, filled with reefs that stretched for hundreds of kilometers. These reefs were not like those of the Silurian. They were vast limestone citadels built by corals and stromatoporoids, sponge-like organisms that created living fortresses beneath the waves. In these reefs, fish ruled with staggering diversity. The seas of the Devonian were home to armored placoderms, elegant lobe-finned fish, swift ray-finned fish, and strange bottom dwellers armored in bone. Among them swam the titans of their age, Dunkleistus, a monstrous placoderm that grew over 8 meters long. Its skull was a fortress of interlocking plates, its jaw armed with sharp bony edges that could crush prey in a single bite. It was the apex predator of its time, ancient nature's first superpredator. But not all Devonian fish were hunters. Some evolved lighter skeletons, flexible fins, and faster movement, giving rise to the ancestors of today's fish. Others, like the lungfish and coelacanth, developed a crucial innovation: lungs and fleshy, muscular fins that allowed them to breathe air and move in shallow water. These adaptations would change the course of evolution forever. The Devonian world was dynamic. In the shallows and swampy estuaries where rivers met the sea, fish began to venture into oxygen-poor waters. Those with primitive lungs could gulp air at the surface, surviving where others could not. Over generations, their fins grew stronger and more jointed, allowing them to push against the muddy bottoms and even drag themselves briefly onto land. Among these pioneers was Tiktaalik, a remarkable creature discovered in Arctic Canada. Neither fully fish nor fully amphibian, Tiktaalik had fins with bones resembling a shoulder, elbow, and wrist, structures that could support its body in shallow water or on land. It could breathe through both gills and lungs, marking the first true transition between water and land vertebrates. It was the prototype of a new lineage, the tetrapods, four-limbed animals that would one day give rise to amphibians, reptiles, mammals, and humanity itself. While vertebrates were finding their way ashore, plants were already transforming the continents. What began in the Silurian as small moss-like sprouts had become, by the Devonian forests, the first in Earth's history. Towering trees like Archaeopteris grew up to 10 meters tall, with true wood and deep roots that anchored into the soil. Fern-like plants, horsetails, and club mosses spread across floodplains and riverbanks, carpeting the land in green. These early forests stabilized the soil, slowed erosion, and released oxygen in vast quantities. For the first time, the air was breathable, and the skies may have turned a deeper, richer blue. The rise of forests also changed the climate. Plants absorbed enormous amounts of carbon dioxide, cooling the planet and triggering new weather cycles. Rain fell more often, carving rivers that nourished the vegetation and filled the seas with nutrients. Insects began to thrive, primitive millipedes, centipedes, and early arachnids exploring the undergrowth. By the Middle Devonian, the land had become alive with the first ecosystems, a mosaic of ferns, shallow pools, and the occasional amphibious fish resting in the shade. It was still a quiet world, but not a lifeless one. The great silence of the continents had been broken. Back in the oceans, evolution continued its relentless pace. The reef ecosystems reached their peak complexity. Brachiopods, bivalves, and corals flourished. Trilobites, though fewer than before, remained common. Predatory ammonites with spiral shells roamed the deeper waters, their tentacles curling like living snares. The Devonian seas were an orchestra of balance and ferocity, a planet in perfect ecological harmony. But as with every age of abundance, the equilibrium would not last. Toward the end of the Devonian, the Earth began to change again. The expansion of forests had drawn down so much carbon dioxide that the planet began to cool. Ice sheets formed at the poles, sea levels fell, and the shallow tropical seas, home to most marine life, began to disappear. Oxygen levels in the oceans dropped, creating vast, dead zones, where few creatures could survive. Between 375 and 360 million years ago, the Devonian world collapsed in a series of extinctions. The coral reefs perished. Most placoderms vanished. Trilobite species dwindled. Over 75% of all marine species disappeared in what became known as the Late Devonian mass extinction. Yet even as catastrophe struck, the seeds of resilience had been planted. The tetrapods survived. The forests endured. In the aftermath of destruction, life had found a new domain, the land. The oceans had been the cradle. The continents would become the stage. From this crisis would rise amphibians, insects, and the first complex land ecosystems. The age of fish had ended, but the age of life on land had begun. Part 12, the Carboniferous world. The age of forests and giants. By 359 million years ago, the world had changed once more. The oceans that had birthed life were no longer its only sanctuary. Plants had conquered the continents, rivers teemed with strange creatures, and the air itself was thick with the scent of vegetation. The Earth had entered one of its most lush and vibrant ages, the Carboniferous period, a time of towering forests, giant insects, and the dawn of terrestrial ecosystems. It was, in every sense, the age of forests and giants. The continents now formed two great landmasses, Laurasia in the north and Gondwana in the south. Between them lay tropical lowlands bathed in warmth and humidity. Vast river deltas and swamps stretched across the equator, endless, steaming wetlands where life flourished in abundance. In these green labyrinths grew the first true forests. Trees such as Lepidodendron, Sigillaria, and calamites rose over 30 meters high, their trunks sheathed in scaly bark and crowned with fern-like leaves. Beneath their canopy spread a dense undergrowth of ferns, club mosses, and seed ferns, primitive plants that would one day give rise to conifers and flowering trees. These forests changed everything. Their roots penetrated deep into the soil, stabilizing the land and transforming the atmosphere. As plants photosynthesized, they absorbed carbon dioxide and released massive quantities of oxygen. By the Middle Carboniferous, atmospheric oxygen levels had soared to 35%, far higher than today's 21%. The very air had become supercharged, and it fueled life in astonishing ways. Insects grew to monstrous proportions. Dragonflies like Meganeura stretched nearly 70 centimeters across, their wings glinting in the humid air. Millipedes such as Arthropleura reached lengths of over 2.5 meters, slithering through the undergrowth like living logs. Giant scorpions and centipedes prowled the forest floor, while early spiders wove silken traps among the moss. It was a world where oxygen itself had become an evolutionary advantage, every breath feeding growth beyond modern limits. But not all giants crawled. Some now walked. Amphibians, descendants of the Devonian pioneers, diversified and spread through the Carboniferous swamps. They came in all shapes and sizes, from small, salamander-like creatures to massive predators like Eriops, whose powerful jaws could crush armored fish and small reptiles. They laid their eggs in the shallows, lived in water and on land, and ruled a world where reptiles had only just begun to appear. The rivers of the Carboniferous were alive with movement. Schools of fish glided between roots and fallen trees. Lungfish burrowed into the mud. Sharks, sleek and adaptive, cruised through dark waters, becoming the dominant predators of the time. The seas beyond the forests teemed with crinoids, brachiopods, and ammonites, survivors from older worlds thriving in stability. The Earth, for once, was in balance. The Carboniferous was warm and wet, its equatorial regions drenched in near-constant rain. Lightning storms crackled over endless forests. The nights glowed faintly with fireflies and mist. It was a time of growth, abundance, and peace. Yet beneath this green paradise, forces were gathering that would reshape the world again. As plants died and fell into the stagnant waters of the swamps, their remains were buried under layers of sediment. Over millions of years, the pressure and heat of burial transformed this organic matter into coal-thick, black seams that would one day power human civilization. The very name Carboniferous means coal-bearing. In these forests, the energy of the sun was locked away, waiting in darkness for hundreds of millions of years. Meanwhile, on land, a new evolutionary breakthrough was taking place. One that would free animals from their dependence on water forever. The amniotic egg. Reptiles had evolved from amphibian ancestors, but they faced a challenge: how to reproduce away from water. The amniotic egg solved it. Encased in a protective shell and filled with nutrient-rich fluids, it allowed embryos to develop on dry land. This single innovation opened the continents to the animal kingdom. Early reptiles like Hylonomus, small, lizard-like creatures, scurried among the roots of trees and hunted insects under the ferns. They were the first fully terrestrial vertebrates, and from them would eventually descend dinosaurs, birds, and mammals. The Carboniferous was a moment of equilibrium, a world both alien and familiar, balanced between ancient swamps and modern ecosystems. But beneath its lush surface, tectonic forces were at work. The continents began to drift together, colliding to form a new supercontinent, Pangaea. As mountains rose and climates shifted, the warm wetlands began to dry. The end of the Carboniferous was marked by change, cooler temperatures, falling oxygen, and the slow decline of the giant insects that had ruled the skies. The vast rainforests began to die back, replaced by drier, sparser landscapes. It was the end of an age of lush abundance, and the beginning of something harder, fiercer, and more dynamic. But evolution was ready. The amphibians would give rise to reptiles. The forests would seed new ecosystems, and life, as always, would adapt to its changing world. The age of forests and giants had ended. Ahead lay deserts, continents of fire, and creatures that would redefine dominance on land. Part 13, the Permian World. The Great Unification. By 299 million years ago, the Earth had once again remade itself. The sprawling swamp forests of the Carboniferous were fading, their humid rain replaced by a drier, harder world. The continents that had long drifted separately now collided to form a single, immense landmass, Pangaea, the first true supercontinent to span pole to pole. This was the Permian period, a time of unity and upheaval. Pangaea was colossal. Its interior stretched thousands of kilometers from the sea, creating vast deserts, mountain ranges, and arid basins. Where tropical swamps once pulsed with life, now there were dunes and salt flats. The climate grew extreme. Scorching summers, freezing winters, and long dry seasons that tested every form of life. But life, as always, adapted. The reptiles that had first appeared in the Carboniferous now diversified across this new, open continent. No longer bound to water, they evolved into a wide array of forms. Swift hunters, armored grazers, and creatures built for endurance rather than abundance. The Permian marked the rise of the reptiles and the slow fading of their amphibian ancestors. In these sun-baked lands walked the synapsids, the mammal-like reptiles. They were the most advanced animals of their time, warm-blooded in function if not yet in form. Some were agile predators like Dimetrodon, a powerful carnivore with a tall, sail-like fin along its back used to regulate body temperature. Others, like Edaphosaurus, were peaceful herbivores, browsing on tough desert plants with grinding teeth. These creatures were the ancestors of mammals, not yet furred, not yet small, but already bearing the evolutionary spark that would one day lead to us. Alongside them roamed other great lineages, the Pariasaurs, squat herbivores covered in bony armor, the Dicynodonts, tusked plant-eaters with beak-like mouths, and the Gorgonopsids, saber-toothed predators that ruled the Permian plains long before the age of dinosaurs. The seas, too, were transformed. The coral reefs of the Carboniferous were gone, replaced by new communities of brachiopods, ammonites, and bryozoans. Sharks diversified again, joined by strange new fish with crushing jaws designed for hard shells. In the shallows, crinoids waved their arms in slow, graceful dances, while plankton filled the sunlit waters. In the deep ocean swam the nautiloids, coiled hunters drifting through warm currents, and the first modern-looking sharks, sleek and fast. For millions of years, the Earth seemed to thrive under its new order: dry lands, diverse reptiles, and stable seas. But beneath the surface, the planet was building toward catastrophe. The formation of Pangaea had created not only new continents but new stresses deep within the Earth's crust. Massive volcanic systems began to stir. As magma pushed upward, it fractured the land and released enormous quantities of carbon dioxide and methane into the atmosphere. Temperatures began to climb. At first, the change was subtle. A few degrees warmer, longer droughts, fewer forests. Then it accelerated. Rainforests vanished. Deserts expanded. Inland lakes and rivers dried up. The once lush landscapes of the Carboniferous were gone, replaced by open plains and scorched rock. By 252 million years ago, the planet teetered on the brink of disaster. In what is now Siberia, a vast volcanic region known as the Siberian Traps erupted with unimaginable force. For 2 million years, lava poured across the land in waves, covering an area larger than Western Europe. The eruptions released staggering amounts of greenhouse gases, driving global temperatures to extremes. The oceans warmed, their chemistry changed, and the very air became toxic. The result was the most devastating event in Earth's history: the Great Permian Extinction. Over 90% of marine species and 70% of land species vanished. Coral reefs collapsed, plankton populations crashed, and the food webs that sustained complex life disintegrated. Trilobites, survivors of every previous extinction, disappeared forever. Forests burned and never returned. Even the insects suffered their only known mass extinction. The skies darkened with ash. Acid rain fell on scorched soil. The oceans turned anoxic, devoid of oxygen, and emitted deadly hydrogen sulfide gas. It was the closest life had ever come to complete annihilation. For millions of years, the Earth was nearly silent. And yet, not everything died. In isolated corners of the world, a few species endured: small reptiles, burrowing amphibians, resilient plants, and microscopic survivors in the seas. From their fragile existence, life began to recover. Slowly, painfully, the biosphere rebuilt itself. In the aftermath of ruin, the survivors evolved to fill empty niches. Among them were the archosaurs, the ancestors of crocodiles, pterosaurs, and dinosaurs. From the ashes of extinction, a new dynasty would rise, one that would rule the next 150 million years. The Permian had united the continents, but it had also reminded the world of a hard truth. Life endures through cycles of creation and destruction. Every rise carries the seed of its fall. Every catastrophe births new possibility. The age of reptiles was about to begin. Part 14, the Triassic Earth. The dawn of the dinosaurs. When the Permian world ended, it took almost everything with it. The forests were gone, the oceans were silent, and the air itself had turned hostile. The Great Dying, as we now call it, had nearly erased the story of life from Earth's surface. But even in silence, the world still turned, and from the ruins, life began again. This was the Triassic period, beginning around 252 million years ago, the first age of recovery after Earth's darkest hour, and the dawn of a new dynasty. The planet that emerged from extinction was unrecognizable. The continents were still fused into Pangaea, stretching from pole to pole. Its vast interior was an expanse of deserts, red dunes, and seasonal floodplains. Only narrow coastal regions and rift valleys provided refuge for life. The climate was hot, dry, and unpredictable, a world of extremes. But in that crucible of instability, evolution flourished. At first, life returned in modest forms. Ferns and cycads regreen the land, while small reptiles and amphibians repopulate the rivers and lakes. But within a few million years, new lineages began to dominate. Among the first to rise were the archosaurs, ruling reptiles, the group that would give rise to crocodiles, pterosaurs, and dinosaurs. Their bodies were built for survival. Strong limbs, efficient lungs, an upright posture that allowed them to move faster and breathe deeper than their sluggish predecessors. At the same time, the synapsids, descendants of the once dominant mammal-like reptiles, continued to evolve. Most had perished in the Permian apocalypse, but a few small survivors endured. These resilient creatures, such as Lystrosaurus, were the hardy pioneers of the early Triassic. They spread across Pangaea, grazing on tough desert plants, and for a time, they ruled the New World. But the balance was shifting. As the Triassic progressed, the synapsids declined, and the archosaurs ascended. By 240 million years ago, Earth was once again alive with diversity. The rivers teemed with fish, the forests echoed with insects, and the skies began to fill with wings. Among the first to claim the air were the pterosaurs, the earliest vertebrates capable of powered flight. With wings formed from skins stretched along elongated fingers, they soared over coastal cliffs and inland lakes, hunting for fish and insects. Below them, on land, the world was changing too. Small, bipedal reptiles began to appear, light, fast, and agile. They walked upright on hind legs, balancing with long tails. Their hips and ankles were unlike anything before, allowing efficient, sustained movement. These were the first dinosaurs, not yet giants but pioneers. One of the earliest known was Eoraptor, a small, agile predator from what is now Argentina. Barely a meter long, it hunted insects and small vertebrates among ferns and cycads. Around the same time lived Herosaurus, a sleek carnivore with grasping claws and serrated teeth, among the first true dinosaurs to rule its ecosystem. At first, dinosaurs were only a minor group among many. The world still belonged to other reptiles, large Rawasuchians that hunted like crocodiles, and sprawling herbivores like Plateosaurus, an early giant that reached lengths of 10 meters and fed on high vegetation. Yet, even as these early giants dominated, subtle changes were underway. The climate grew wetter, and volcanic activity split Pangaea apart, forming rift valleys that would one day become the Atlantic Ocean. New coastlines and habitats appeared, creating opportunities for evolution to experiment again. The Triassic ecosystems became more complex. Reptiles filled every niche. Swift insect eaters, massive herbivores, aquatic predators, and sky gliders. Amphibians, once rulers of the Carboniferous, now lingered at the edges of swamps and lakes. And small, warm-blooded synapsids, precursors of mammals, crept through the undergrowth, surviving in the shadows of the reptilian empire. In the oceans, life recovered as well. New species of ammonites spiraled through the currents. Ichthyosaurs, dolphin-shaped marine reptiles, returned to the seas as swift, powerful hunters. Later came nothosaurs and plesiosaurs, long-necked swimmers that glided through the shallows with elegance and precision. For 50 million years, this new balance held, a vibrant, evolving world under alien skies. The Triassic was not yet the age of dinosaurs, but it was the forge that created them. Then, once again, disaster struck. Around 201 million years ago, as Pangaea continued to tear apart, volcanic activity erupted on a scale rivaling the Siberian traps. Across what is now the Atlantic, the Central Atlantic magmatic province spewed millions of cubic kilometers of lava, releasing vast quantities of carbon dioxide and sulfur gases. Temperatures soared. Oceans acidified. Another mass extinction swept the planet, the fourth in Earth's history. Most large amphibians and many rival reptiles vanished. Entire ecosystems collapsed. But once again, certain survivors endured. The dinosaurs, small and adaptable, emerged from the crisis stronger than before. With their competitors gone, they spread across the continents, filling every vacant niche. In the air, pterosaurs multiplied. In the seas, ichthyosaurs and plesiosaurs thrived. On land, the world belonged to the dinosaurs. The Triassic had begun in desolation and ended in dominance. From the ashes of extinction, a new age was rising, one that would last for over 160 million years. The Age of Dinosaurs had begun. Part 15, The Jurassic World. The Empire of Giants. When the Triassic ended, the Earth was once again remade by fire. The continents had begun to drift apart, splitting the great supercontinent of Pangaea into separate lands. The Atlantic Ocean opened as molten rock welled up between the rift plates, and the climate, once dry and harsh, softened into a warm, wet, oxygen-rich world. From the ashes of the Triassic extinction arose a new, astonishing age, the Jurassic period, beginning around 201 million years ago. It was a time of recovery, of expansion, and of giants. The Earth was greener than it had been for millions of years. Moist tropical air circled the globe, feeding vast jungles of conifers, cycads, and ferns. Rivers wound through valleys alive with the cries of reptiles, and towering volcanoes rose along the edges of growing oceans. The biosphere had stabilized, and life responded with a surge of diversity unlike anything before. This was the world where dinosaurs became rulers. Across the newly separated continents of Laurasia in the north and Gondwana in the south, dinosaurs filled every niche. They grew larger, faster, and more specialized, their dominance unquestioned. Among the herbivores, new giants appeared, the sauropods. Creatures like Diplodocus, Brachiosaurus, and Apatosaurus stretched over 25 meters long, their necks sweeping through the canopy like living cranes. They moved in herds, shaking the ground as they walked, feeding constantly to sustain their vast bodies. Some could rear up on their hind legs to strip leaves from trees 6 stories tall. Their size was both a defense and an advantage. Few predators dared challenge them. But there were hunters bold enough to try. The Jurassic saw the rise of the great theropods, carnivorous dinosaurs that perfected the art of pursuit and ambush. Among them was Allosaurus, the apex predator of the late Jurassic, sleek and muscular, armed with serrated teeth and curved claws. It hunted in packs, bringing down prey many times its own size. Smaller theropods, agile and intelligent, evolved sharper senses and faster reflexes. Some developed feathers not for flight but for insulation and display. In these swift, bird-like predators lay the seeds of a future transformation. The Jurassic forests were lush and endless. Ferns and cycads covered the ground, while towering conifers stretched toward a sky thick with humidity. Insects buzzed through the canopy, and dragonflies glimmered above ancient ponds. The air was warm, the nights alive with the calls of creatures that had never known extinction. And overhead, another revolution had taken flight. The pterosaurs, those early flying reptiles, now dominated the skies. Species like Pteranodon and Rhamphorhynchus soared on wingspans up to 10 meters across. They hunted fish in coastal lagoons, skimmed waves, and nested on rocky cliffs. Some had crests of brilliant color, used for display or thermoregulation, prehistoric banners waving in the wind. Below them, a new kind of animal was taking shape among the smaller theropods. Covered in down like feathers, some began to glide between trees. Others developed true flapping flight. By the middle of the Jurassic, the first birds had appeared, like Archaeopteryx, a creature halfway between dinosaur and bird, with feathered wings and a long reptilian tail. It was a bridge between worlds, a symbol of evolution's continuity, a living echo of the age before and the age to come. The oceans, too, were alive with giants. Vast marine reptiles patrolled the seas. Plesiosaurs with long necks and paddle-like limbs. Pliosaurs, shorter but more powerful, with jaws as long as a man. And ichthyosaurs, sleek as dolphins, built for speed and endurance. Shoals of ammonites, the spiral-shelled cousins of modern squids, filled the oceans with motion and color. Coral reefs returned in abundance, and fish diversified into new shapes and sizes. The Jurassic Earth was a planet of abundance, warm, stable, and rich with oxygen. For nearly 60 million years, it knew no mass extinction, no global freeze, no famine of sunlight. Evolution thrived in peace, and the dinosaurs perfected their empire. But beneath the surface, slow tectonic shifts were already sowing change. The continents drifted further apart. Sea levels rose. New mountain ranges formed, altering winds and rainfall. The planet was stirring again, preparing for another chapter. One that would bring new landscapes, new creatures, and new catastrophes. The Jurassic world was the age of balance. Immense but harmonious, wild yet stable. For a moment in deep time, life seemed unstoppable. Yet even empires of giants cannot last forever.